Hello class, in this module we are going to focus on another way of finding our enthalpy of reaction. Now before we went and found our enthalpy by using the coffee cup calorimeter, and then we learned about Hess's law. So let's go ahead and now tackle the third way, and we're going to be using what are called standard enthalpies of formation. So let's focus on the word standard first. The standard state, or our standard state, it's the state of our material, and we're going to define it using a set of conditions. Well, the conditions are as follows. Our pure gas, the conditions are 1 atm. For our pure solids and liquids, the temperature is going to be 25 degrees Celsius. And for solutions, it's going to be 1 molar. Now, our standard enthalpy change, that change that takes place is going to be when all of our reactants and products are in their standard states. They're going to be in their standard states. So they are at those conditions. Now, how do we know that that's happening? So here we have the delta H, and I hope you notice there's a degree sign there. The degree sign lets us know it's in its standard state. So it lets us know it's in its standard state. Now, the standard enthalpy of formation is when we have an enthalpy change for the reaction forming 1 mole of a pure compound from its constituent elements. We're going to describe that further in an example, but it's useful to know that for a pure element in its standard state, our delta H is going to be 0. So let's look at this table. So this is a short table in your chapter, but also there are more in Appendix 2. So you can find more of your enthalpies of formation here, your standard enthalpies of formation. So let's go ahead and take a look. And I just want to point out that bromine, we know it's a liquid. There is it, and it's in its standard state, it's 0. And let's look at carbon. So graphite, that's the pure element in its standard state, that's 0. And then I wanted to point out sodium, there you go, that's a solid, and that's 0. And sulfur, so I mentioned a couple of weeks ago that, or to refresh your memory, that sulfur exists as S8. And this is why I was pointing out sulfur and even phosphorus. That for phosphorus it's a P4, and that's because of this chapter and this section. So it would be 0. Now let's go ahead and take a look at what it means by forming 1 mole of a pure compound from its constituent elements. So we're going to look at ammonium for this. All right, now, so we want to know what is the delta H of formation. So that's for an ammonium hydroxide that is formed from its constituent elements. And how much do we, by definition, how much of our ammonium hydroxide? 1 mole, right? 1 mole. So let's go ahead and take a look at that. So if we want 1 mole, well, I don't need to write the mole, 1 of our ammonium hydroxide, then what are the constituent elements? And that's what I really wanted to point out here. So we could look up this delta H of formation. That's going to be in a table in the appendix. So when I say what is the delta H of for our ammonium hydroxide, I'm actually not going to calculate that. I'm just showing you would look that up in the table. But what I want to point out is the constituent element part. So forming ammonium hydroxide, what would you have needed for your reactant? Well, if we have nitrogen, we would have needed N2. So that's what they mean by the constituent element. So what are the elements that were needed to go ahead and form ammonium hydroxide? So we know N2, and we also know that we have a hydrogen there. So what would that have come from? It had to have come from hydrogen gas. And then finally oxygen. So that would have come from oxygen gas. And because this is, the definition is 1 mole, then we would have to balance our reactants only, because this 1 can't change. So if we have 1 nitrogen there, we know that this would have to be a half. If we have 5 hydrogens, then we know that this would have to be 5 halves. And then we have again 1 oxygen, so that would be a half. Okay, so again, what I want to point out is we could look up our delta H formation for ammonium hydroxide in a table, but we already know our delta H's of formation for our constituent elements, and that would have to be 0, right? So in its elemental form, we have nitrogen as N2, so that would be 0. This hydrogen would be 0, and this oxygen would be 0. So pure elements in the standard states, again, are 0. So here's just a table to refresh your memory for some common constituent elements. So we have, again, I pointed out earlier, sulfur, carbon graphite, iodide's a solid, right? So I broke this up into gases, liquids, and solids for everyone. Okay, now let's go ahead and use our heats of formation in their standard states and trying to calculate our enthalpy change. Before we do this, I have to give you guys a new formula. So the formula used for this is our delta H is going to equal our sum of our heat of formation, standard heats of formation of our products, minus the sum of our standard heats of formation of our reactants. So it's products minus reactants. Okay, so let's go ahead and apply that to this problem. Now, before we do anything, before we determine our delta H, we have to balance our equation first. So I'm going to rewrite this. So NH3 plus O2 goes to NO2 plus water. So if we balance this, we're going to get 4 ammonia here, 4 here, we get 6, and then we're going to get 7. Okay, now let's take a look at how we're going to do this. So first, we're going to write out our delta H for our reaction. And here, we know it's going to be the products minus the reactants. But what do we have to know first before we do the calculation? We have to look up our delta H, our heats of formation, our standard heats of formation in the table. Again, that's in Appendix 2. So I have to give you these. These are something that you are not going to memorize. So if I look through here, I know one already that I can write in, because I should know that oxygen, pure element, that is going to be 0. The rest I have to look up in the table. So here I've looked them up in the table, and the units are kilojoule per mole. So for ammonia, I got minus 46. For NO2, I found that it was 34. And then be careful when you look this up, especially for water. There's liquid, solid, and gas, so pick the one for gas, and that's minus 242. Okay, so now I can actually plug it into that formula. So my delta H of my reaction, products minus reactants. So the products, I'm going to start with NO2 first. I have 4 of them. So you have to take into consideration the coefficients. So you need to multiply these by the coefficients. So let me write that. So you need to multiply by the coefficients. Okay, so that's where that 4 came from. And now I have 4 times 34. So that's from my NO2. Now the next product I have 6 waters. So then I'm going to add 6 because I've got 6 of them, and then it's delta H minus 242. And then I'm going to close that bracket. So now we finished the products. So let's go ahead now and take a look at the reactants. Erase that so it looks nicer. So now let's focus on the reactants. So the formula is minus the sum of our heats of formation in the standard states. So I start the minus, and I'm going to write a new bracket for the reactants. And here I'm going to start this over here. Now, how many do I have? We've got 4. And for ammonia, minus 46. That looks messy with this pen. Okay, minus 46. And then we know that we've got 7 oxygens, but again, it's 0. So we're going to just multiply that by 0. So this whole thing just cancels. Okay, now let's go ahead and do the math. So I'm going to equal, and I'm going to do the product side first. And I get minus 1316. And then I'm going to subtract from the reactants, which is minus 184. Now you need to put a minus 46 there. And then close that. So everyone, I hope you saw I wrote 46 and I forgot to include the minus. I'm sorry, I don't want to video this again for time, so just put the minus in there. So now if we do this, we've got 1,132 kilojoules. All right, so hopefully that was clear. So I want to do it one more time. I'm going to go through it. So products minus reactants. The products, I've got 4 NO2s, 4 times 34, 6 waters, 6 times negative 242. And then subtract the reactants, I've got 4 ammonia, so 4 times, and again, this is a negative 46 plus 0. Okay, and then finish the math, you should get 1,132, and it's minus. We're going to get a minus, so it's exothermic. Okay, I hope that's helpful. On to the next module.